Good morning, ladies and gentlemen. Let's go ahead and tell whether or not the series converges or diverges. And we have a wide range of different tests that we now can apply. The question is, which test is most appropriate? All right, so as I look at that first one, it looks very similar to, right? It looks very similar to a series that I know about convergence or divergence. On the bottom, we see we have n to the first times n to the 1/2 is n to the 3/2. Right? This is a p series where my exponent, 3/2, is that greater than or less than 1? Greater than. So does 1 over n to the 3/2 converge or diverge? Converges by the p series test. So all I'm going to do for the first one is just pull, oh goodness, I'm going to orient the smartboard. So all I'm going to do is rewrite the original as 3 times n equals 1 to infinity of 1 over n root n. And the reason I did that is because now we just have a constant times a series that I know converges by the p-series test, therefore my original also converges. Remember that constant times doesn't change the convergence or divergence at all, bless you, it would just change the magnitude of that finite value the series converges to. Therefore, this converges by the p-series test. And we can go so far as to say that p equals 3/2 is greater than 1. So who got convergence for the first one? Convergence? And who used the p-series test? Great. Awesome. Let's take a look at the second one. So I saw some people going with ratio tests, right, which is a very powerful test. I didn't see anybody doing limit comparison, but some of you might have tried that I didn't see. However, as you look at your original fraction, as n goes to infinity, consider what the nth term does. And I see that as n goes to infinity, my nth term is going to approach 2 over 1 is 2. And so if the nth term, right, approaches 2, there's no hope of the original series converging. In order for a series to converge, a necessary precondition is that the nth term goes to 0 in the limit. Therefore, this series diverges by the nth term test, and we don't have to go and find a series for comparison. So, the limit as n goes to infinity of the nth term does not equal 0, so the original diverges by the nth term test. It's important to note that the nth term test can only use to show divergence. We can't use the nth term test to prove convergence. It's just a necessary condition that the nth term approach 0 in order for there to be some possibility of convergence at all. However, it's the quickest, the nth term test is the quickest, most direct way to show divergence of a series. Raise your hand if you had divergence for number 2. Did you already have that? So we're 2 for 2. Let's take a look at number 3 then. In number 3, we've got a rational expression where I've got really polynomial top and polynomial bottom. So I can rely on my knowledge of n behavior to select a series, right, for comparison. So in my head, I'm thinking that in the long term, as n goes to infinity, I bet the nth term is going to behave like n over 2n cubed is 1 over 2n squared. So I'm thinking that this is going to behave like 1 over 2n squared, which, like number 1 from the Bellwork, is a p-series, right? What do we know about series B? If we let that be 1 over 2n cubed, I'm sorry, 1 over 2n squared it'll be? Well, we know that this converges by the p-series test because my exponent is greater than 1, right? So if I let series B, if I think that that original is going to behave like 1 over 2n squared, I'll go ahead and select the limit comparison test and use this as my series to compare it with, right? I know that if I perform the limit comparison test and get a constant, then my original and my chosen series of comparison share the same fate. I know this converges, so I'm going to do the limit comparison test, see if I get a constant, and I'm going to say they share the same fate. Everyone say no? Yeah?
Do you have to do the 1 over 2n squared, or could you do 1 over n?
You could do 1 over n squared. Yeah, absolutely. So you could do 1 over, oh, yes. I think it behaves like this. In fact, let's use 1 over n squared because that'll be easier for the algebra. Okay, so I'm going to use 1 over n squared. I was thinking that the nth term goes like that because we can see that, right? Easier. And some of you could use this then do direct comparison too, by reasoning that that 2 is going to make the denominator larger, which makes the overall value smaller. So that opens up a new test. Great. So let's go ahead and do limit comparison. So for my limit comparison test, I'll consider the limit as n goes to infinity of the ratio of original to new. So I'll let my original be series A, n plus 4 over 2n cubed minus 1. And then I'm going to divide by my chosen series of comparison. That is 1 over n squared, which I know to converge by the p-series test. But dividing by this fraction, 1 over n squared, is the same as multiplying by n squared over 1. So I'm going to go ahead and do some algebra and see what happens. N plus 4 times n squared is going to be n cubed plus 4n squared all over 2n cubed minus 1. And as n goes to infinity, right, I see that the dominant term on top, 1n cubed, over the dominant term on bottom is 2n cubed through L'Hopital's rule, or through algebraic simplification, that is maybe dividing every single term by n cubed, the largest power of n that appears. I'm going to get 1/2. Do you guys see that? So we'll get 1/2, and you can do either of those. I've been kind of liking this algebraic. Let's do that. According, it looks like I get 1 plus 4 over n all over 2 minus 1 over n cubed. Now it's easy to see that each of those fractions is going to go to 0 in the limit. So I'll get a limit of a constant. 1/2 is the constant. 1/2, and this is a constant. Therefore, since the limit of the ratio of the nth terms in the series is a constant, they share the same fate. Since my chosen series for comparison converges, my original series converges by limit comparison. So we should say awesome. I'm going to say my chosen series converges by p-series. So if they share the same fate, the original converge by the comparison test.
Mr. Next, do we have to say that the 1 over n squared one converges because it's a p-series?
Yeah.
Or is that like everyone should know that, you know?
I think you should say it. Awesome. Question you guys have about number 3. Important point was brought up. Do you have to use limit comparison test? No. We could have done direct comparison if we chose 1 over n squared as series B. We could make a case for series A, the nth term being less than or equal to series B, right? For all n greater than or equal to some positive integer n. Once that nth term gets smaller than this forever after because of that multiplier 2 on bottom, then we could use direct comparison because my original is forever less than or equal to my known series which converges, so it would be forced to converge as well. Ah, that's pretty sweet. All right, we'll go ahead and pause the recording and take care of our OTL number 9 check. Okay, ladies and gentlemen. So today we're going to attack the difference between absolute convergence, right, versus conditional convergence. And this is going to be a key feature when we go to consider the endpoints, right, over the interval in which a series converges. So let's go ahead and remind ourselves that if the sum of the absolute value of my terms, right, converges, then the original series must converge as well, it converges absolutely. And absolute convergence is the strongest type of divergence. Absolute convergence guarantees convergence. And so if the sum of the absolute value of the terms converges, then the original series converges as well. However, a series may still converge, just not converge absolutely. Such a series is said to converge conditional. The definition of absolute versus conditional convergence is as follows. The series is absolutely convergent if the sum of the absolute value of the terms, that is all positive terms now, converges. Right? So if the series of the positive, right, the absolute value of the terms converges, then the original series converges absolutely. Series A is conditionally convergent if the series converges, but the series of the positive terms, that is the absolute value of the terms, diverges. And so if it doesn't converge absolutely, but it still converges, it's called conditionally convergent. And we'll see that while that converges, it's just not as strong a case of convergence. So if the sum of the magnitude of the terms converges, then the original series is absolutely convergent. If it converges, the series converges, but it doesn't converge absolutely, then it converges conditionally. And we'll see that's an important distinction. That's for you. Let's go ahead and determine whether each of the following is convergent or divergent. We'll furthermore classify any convergent series as absolutely or conditionally. So let's go ahead and take a look at this brand new series. We haven't seen this before. Or have we? As I look at those terms, negative 1/3, negative 1/9, plus 1/27, plus 81st, is this, bless you, an alternating series? To be an alternating series, right, each successive term must alternate in sign. Does this? No. And so while we switch from positive to negative, and we'll continue to do so, right, based on which term we're talking about, it's not an alternating series. So I can't apply the alternating series test. However, I can consider the absolute value of the terms. It's not an alternating series. But as I consider absolute versus conditional convergence, right, I'll go ahead and consider the sum from 1 to infinity of the absolute value, basically. And in doing so, I see the absolute value of negative 1 to the whatever is going to be positive 1. And the denominator is 3 to the n. And that simple rewrite allows us to recognize this as what type of series? Geometric, with r equals 1/3. Therefore, since the series of the absolute value of terms converges, the original converges absolutely, and that's the strongest type of convergence. So this is geometric with r equals 1/3, which is less than 1, so converges. And because it converges, the absolute value of terms it converges absolutely, and the original converges. Absolutely. All right, so we're 1 for 1 in terms of the convergence world, right? That's cool. Let's take a look at another. Consider the series given by the sum from 1 to infinity of negative 1 to the n, that's just my alternating, right, positive, negative, over the natural log of n plus 1. Right? And so let's consider what's going on here. Firstly, do I have an alternating series? Yes, because it's just -1 to the n, that guarantees I'll have positive, negative. Natural log of n plus 1 is always going to be positive for my n increasing inputs. So I have an alternating series in, I'm sorry. Yes, the terms alternate in sign, right? In order to apply the alternating series test, I have 2 more prerequisites to consider. So let's go ahead and see. I've got terms alternating sign. So it is an alternating series. My second requirement is that the term values decrease in magnitude. Let's go ahead and consider the terms here. ln1, no, it's not there. ln2, ln3, ln4, ln5. So what's happening to my denominators? They're getting larger, right? Slowly. ln5, ln6, getting slowly larger, which means that and the top is staying at 1, which means that the overall value of the nth term is shrinking, right? And so, yes, the terms decrease in magnitude. Check. Look at that too. Let's say. Terms decrease in magnitude, and our third requirement is that our nth term must go to what in the limit? Well, my nth term must go to 0 in order to apply the alternating series test for convergence, right? And say that it does. And it looks like yes. The denominator will continue to grow. The top is fixed at 1, so the nth term does go to 0. So I've got to check. So this converges, right? This converges by the alternating series test. Well, that's great. But we need to say if it converges absolutely or if it converges conditionally. So what's the distinction? Bless you. Well, we need to consider still, and we could have done this first, right? There's no order. We just need to consider both cases. We need to consider if the sum of the absolute value of the terms, right, converges. If it does, then it converges absolutely. If it doesn't, then it converges conditionally. So we have to consider now. Good job. The sum of the absolute value, right, of the terms. And as we do that, what happens to that numerator, right, -1 to the n, if I consider those terms in absolute value? It's just 1 all the time, so my top is always 1. My bottom then is ln of n plus 1. So when I consider the series in absolute value, right, the alternating portion stops. It's always +1 over. And now, what do we think happens? Well, consider the denominators, right? My denominators here, ln2, ln3, ln4, ln5. Well, those are getting larger, means my terms are getting smaller. Yes? The question is, are they getting smaller fast enough for the overall value of the series to converge? Right? Like at our original discussion when we talked about is the nth term approaching 0 fast enough to ensure that the sum of the terms is approaching a finite value, or do we continue adding on too much? So what are we going to do? Well, I don't know specifically how ln behaves, but I can compare it with the known series, right? What is this similar to? What series do I know about? I know about 1 over n, right? Let's go ahead and consider the harmonic series, 1 over n, and let's compare the denominators. The natural log of input versus input, right? How do those compare? That is a linear function versus a natural log function. How do they compare? Yeah, the natural, this harmonic series, right, n is greater than natural log of n, which means that my smaller denominator creates overall term values that are larger than the harmonic series, which we know to diverge. Therefore, if my original series has larger terms than a known series of divergence, what can I conclude about the original? It must also diverge. And so this is by direct comparison. And so because I'm comparing the denominators of nu with the denominator of the harmonic series, these denominators are smaller than n, ensuring the fraction will be greater than or equal to the value of the terms in the harmonic, which is known to diverge so the original series does not converge absolutely, and yet it does converge. Therefore, what type of convergence is it? Converges conditionally. Converges conditionally. So if a series converges but does not converge absolutely, it's said to converge conditional. Okay, it's said to converge conditional. Marissa.
I have a question about the alternating series test. So if you only met like one or two of those things, can you say diverges right away, or does that take you like you have to take another test?
You have to take another test. Yeah. Those prerequisites are for you to apply the alternating series tests to show convergence.
Yep.
If you fail to satisfy any one of the three or more, then you can't use alternating series tests to show convergence. But it could still converge. You just have to look at something else. Okay. So what are we going to do now for 3? Oh, goodness. Do I have an alternating series? Yep, the terms alternate in sign. Do the magnitude of the terms decrease? No. Look at the nth term. 0 factorial over 2 to the 0 is 1. 1 over 1 plus 1/2 plus 2/4 is 1/2. Sorry, minus. So I have terms that alternate in sign, but the nth term here, what's on top? I've got factorial on top and exponential on bottom, right? Who grows more quickly, factorial or exponential? Sydney.
Factorial.
Factorial is our new top dog in Growth Town, right? So factorial is the fastest growing thing now in the limit as n goes to infinity. So what happens? Well, my nth term does not approach 0, so this is not going to converge at all. It won't converge conditionally, it won't converge absolutely. This diverges by the nth term test. So this diverges by the nth term test. Gosh, bless you. I like the nth term test. That's quick, right? So if the value of the nth term doesn't approach 0, then goes to infinity, then right away we can say it diverges by the nth term test. So that's pretty sweet. Okay, let's go ahead and take a look at another. Last time we went ahead and considered the alternating series prerequisites first. You want to go ahead and take a look at the absolute value first this time and see if that's a more efficient way. We can consider the series and absolute value. Okay. So let's go ahead and consider the limit of the series and absolute value to see whether or not this absolutely converges or not. So we'll have the series and absolute value. That will be given by the sum from 1 to infinity of. Thank you. That would be the 1 over square root of n. Yes? And would this converge or diverge? Converge? Diverge? Tastes great? Less filling? Why? Yeah, this is a p-series with n equals 1/2, which is less than 1, so diverges, which doesn't mean the original series diverges. It means that it does not converge absolutely because we were considering the series in absolute value. So we know that this does not converge absolutely, so this diverges by p-series with p equal 1/2, which is less than. Well, does that mean that the original series diverges? No, it just means that it doesn't converge absolutely. So we now still need to consider the original. So original. Can we do 1, 2, 3? Marissa, let's do 1, 2, 3. So what's our 1? Do the terms alternating sign. Yes, so we've got alternating sign. Check. Do the terms decrease in magnitude. Yep. So the terms decrease in magnitude. Again, decrease in magnesium. No. Decrease in magnitude. Good. And is the limit of the nth term 0? Yes, the nth term goes to 0 in the limit. So that's good. Great. So we've got a check, check, check. Which means what? It means the original converges by alternating series text. Since it does not converge in the absolute value, this converges conditional. You guys see that? So this converges, the original converges by alternating series test. So it converges by alternating series test, but because the series and absolute value diverge by p-series, the original converges conditionally only. It does not converge absolutely. Conditionally. Awesome. What questions are you guys having on alternating series? Sid?
I just have a question on this one. So we figured out with the p-series that it doesn't converge absolutely.
Yes.
Then why do we need to see if the criteria is met for the alternating sign? Like, can't we just, if we know it doesn't converge absolutely, can't we just say it converges conditionally?
No,
No?
because the original, right, the original might diverge. So just because it doesn't converge absolutely doesn't mean it converges conditionally. If a series diverges, it doesn't converge absolutely. So just showing that it doesn't converge absolutely doesn't mean it converges conditionally. It could still diverge.
Okay.
Number 3. Does number 3 converge absolutely? No. Does it converge conditionally? No. It diverges, period. So remember, to be conditionally convergent, we have to have a converging series that just doesn't converge in the absolute value. Okay, so who cares? Right? Why do we make a distinction between absolute versus conditional convergence? Isn't it enough to just know whether or not a series converges or not? Well, it turns out that those two types of convergence, right, are very important for 2 different reasons. The first of which is what we call the rearrangement of terms in a series. And so I want you to go ahead and think about a series as representing a sum of terms. We have finite sums. Here, perhaps with an overly simplified example, consider the sum that's finite, -4 plus 6 minus 7 plus 10. Some of you are already out there and going faster and faster. And what'd you get, Riley? 5? Yes, 5, everybody? Well, what if we instead had 10 plus 6 minus 7 minus 4? All right, I'm going to do my best to exhibit good wait time. What do you get for that? Tyler? 5 also get 5, yes? And so if we have a finite sum, we could rearrange the terms in whatever order we want without affecting the value of the sum. It's always going to be 5, right? So long as my negative belongs to the 7 and the negative belongs to the 4, right? Which it does. Yes? Okay. That's not necessarily the case with infinite series, right? Where I have an infinite number of terms that continue going on and on forever. Only an absolutely convergent series can be rearranged in any order and still produce the same sum. And so if I have an absolutely convergent series, that is one where the sum of the absolute values, all positive terms, converges to some finite value, right? Then I could rearrange those terms in any order I want and not change the value of that sum. It would be the same thing, right? However, a conditionally convergent series can be rearranged so that it diverges. Or even so it converges and equals any predetermined sum desired. What? If a series, a convergent series, is only conditionally convergent, we could rearrange the terms to make it diverge. Or we could keep that conditionally convergent series as a converging series and just make it converge to any sum that we wanted to. Let's take a closer look at this. This is interesting. So, that's for you. So, a classic example is the alternating harmonic series. And so what we want to think about here, right, is in order for a series to converge, the limit of the partial sums must converge to a value. And the other day, we examined this geometrically. We started at 1, right? And we plotted S sub 1, the first partial sum, and then we plotted S sub 2, which was 1 plus 1/2 is a half, and then we plotted S sub 3, which now went over a third, and then back and forth, and then over a fifth, and then back a sixth, and we saw that the limit of the partial sums, right, was converging to some particular value, and since the limit of the partial sums existed and was a finite number, then the series must converge as well. Well, not so, right? Not so if we have the absolute value, right? If we had the absolute value, then this would be what series? The harmonic series, which we know diverges. And so let's go ahead and take a look with this conditionally convergent, right? Because it converges, right? The series converges, but because the limit of the partial sums converges, this converges by alternating series test now too. But it diverges in the absolute value, so this is not absolutely convergent, it's conditionally convergent. All right, let's consider rearranging the terms to equal the number e. Or pi. We could rearrange the terms to equal the transcendental number pi. I want you to go ahead and think about the partial sums with me. And so what we're going to do is we're going to take these same terms that are in this conditionally convergent series. Let's start, but let's only grab the positive ones. And so we're going to go ahead and scan through here, and we're going to start with the positive ones. And we're going to only grab the positive ones in order, the next one that we grab, until we go above the number e. And so we're going to keep grabbing positive term values until our partial sums is greater than e, right? Now we're going to go ahead and we're going to start grabbing negative terms. We're going to go back now, and now we're going to do a bunch of negative terms so far. Just negative terms. So that we pull that partial sum, right, back beneath the value of e. Okay? So we first used positive ones to get above e. Then we went ahead and started at negative terms until we got below e. And now what are we going to do? Well, now we're going to go ahead and grab some more positive terms from my infinitely long series. and we're going to add those terms until we get above e again, right? And then what are we going to do? Well, now we're going to grab some negatives, and we're going to get below e as we add those negatives. But all the while, these terms are decreasing in their size, and so my partial sums are, there's my number e. They're here, and then 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 they're here. Do the limit of the partial sums, right? Do the limit of the partial sums approach a particular value? Yes, as I continue adding terms, as n goes to infinity, the limit of the partial sums is set up to converge upon my number e. And we can set this bar at whatever predetermined sum we wanted. And so by taking a conditionally convergent series and rearranging the terms, right, how we want to, we can make it equal any predetermined sum. We could also rearrange them to diverge. So let's start over. Oh, again, we only have these terms to work with, right? We only have these terms to work with, but there's an infinite number of them. And so it's all about the limit of the partial sums. If the limit of the partial sums converges, then the series converges. If the limit of the partial sums does not converge, right, to a finite value or doesn't exist, then the original series diverges. So now let's construct it so that it diverges. We only have these terms to work with, but let's go ahead and add positive, right? Add positive terms until we get high. Oh, I don't want that high. And then negative terms until we get a little bit more negative. And then positive terms until we get a little bit more positive. And then negative terms, as many as I need, until we get more negative than my last positive was, and so on and so forth. And remember, if, as n goes to infinity, do the partial sums approach a particular value? No, we set it up so that my partial sums, right, are not approaching a particular value, and if my limit of the partial sums do not approach a particular value, if that limit does not exist, then the original series must diverge. So if we're dealing with a conditionally convergent series, we can rearrange the terms to either diverge or to equal any predetermined sum. Notice how neither one of these scenarios is possible if the original is absolutely convergent. How come? Because I no longer have any of those negative signs. I can't pull back that sum towards a predetermined value or farther away, right, from that center line. If it's absolutely convergent, then I only can work with positive terms, and so no matter my rearrangement, I'm always going to approach that same finite sum. Okay, so that's the difference between absolutely and conditional. Pretty cool. Interesting. Interesting though. All right, the last thing we need to do in our unit, right, is to check the endpoints for some interval of convergence. And so we spent a lot of time back at the beginning with our Taylor series, and when we were constructing our power series and our expansions and familiar functions, talking about this interval of convergence, but never really attacking those endpoints of the interval. So on a practice free response question that was specific to BC, the last time they had you find the interval of convergence and test the endpoints, and they ended up using the ratio test to do so. But we're going to go ahead and check the endpoints on my interval of convergence to see whether or not we include that x value, right, with square brackets, or if it's excluded with parentheses. And that's the last thing we have to do in our series unit. Determine the exact interval of convergence for each series. For what values of x does the series converge absolutely versus conditionally? So we'll go ahead and take a look at the original. And like Bellwork, we can try and see if we can compare this to any known thing. Well, I've got x's in it, right? I've got x's in it here, so this is going to be a power series. And we know that the ratio test will allow us to determine the interval of convergence, right, for a power series with x's in it. I can go ahead and consider that ratio, and then with the absolute value set less than 1. And then I know if my ratio of the a sub n plus 1th term to a sub n is less than 1, then it's going to converge. So let's go ahead and start with the ratio test. The ratio test with absolute value bars, right, will then give us an interval on which the series converges absolutely. How come? Because we're going to do the absolute value of the ratio. So let's consider the limit as n goes to infinity of x to the n plus 1 over n plus 1 times, so dividing by the original would be multiplying by the reciprocal. I get n over x to the n. Are you guys getting that? That in turn is given by the limit as n goes to infinity of, and again, you don't have to pull this out front. Can I go right to that x times x to the n over x to the n is x? After our last OTL, did you guys practice doing that a lot or no? Do I do one step in here? You okay? All right. So this is x times x to the n over x to the n is just x on top. In order for this to converge absolutely, this, right, must be less than 1. However, I still have these n's to deal with. As n goes to infinity, what happens to this fraction n over n plus 1? Cindy? It goes to 1, right? You could do L'Hopital's rule. The derivative of n over n plus 1 is 1 over 1. It goes to 1. You could do down a term. You could do algebraic, divide everything by n. All right, which means that I need absolute value of x to be less than 1, right? Which means my radius of convergence is 1. My interval on which the function converges, right, would be negative 1 to 1, but I have to test my endpoints. So let's go ahead and consider my endpoints. In order to do this, I'll simply plug in that x value from my interval of x values into the original, and then use one of my tests to see if that particular series would converge or not. So let's go ahead and consider negative 1. Negative 1 into my original would create a new series. The series would be, I'm going to label it. So at x equals negative 1. My series is negative 1 to the n over n. Is that right? Negative 1 to the n over n. And negative 1 to the n gives me the alternating sign, doesn't it? And so my first term would be negative 1 plus 1/2, yes? Minus 1/3 plus dot dot dot. And so here's the opposite of the alternating harmonic series. However, we know that this series does what? Does it converge or diverge? Converges, right? Diverges in the absolute value. We just determined at that endpoint that this, right? At this endpoint, we get a convergence by what test? Marissa, 1, 2, 3. Do the terms alternating sign? The terms decrease in magnitude. Is the limit of that term 0? So at x equals negative 1, the series converges. So we include it in my interval of convergence, and yet it converges conditionally when x equals negative 1. So this would be a particular value of x where it converges conditionally. So my interval of convergence we know so far is square bracket negative 1 comma to 1. Now let's test at x equals 1. Yes? At x equals 1? At x equals 1, what's my series? Well, I go to my original, right? And when x equals 1, my series is one to the n, which is what series? The harmonic, which diverges, right? And so this is not conditional convergence. It is divergence, which means this x value is not included on the interval of convergence. This diverges, so I do not include positive 1 on the interval, and I show that with parentheses. So my exact interval of convergence is negative 1 inclusive to positive 1 exclusive, right? The series diverges when x equals 1. I'm going to write divergence here. All right, so I have the exact interval of convergence. Now I need to consider for what values of x does the series converge absolutely. The series converges absolutely when we did the ratio test and got when x is less than 1 strictly. So the series converges absolutely for strictly -1 to 1, conditionally for x equals -1, and not at all for x equals +1, right? So let's go ahead and say something like absolutely for what values of x, -1 to 1, conditionally -1 is on the x value, right? Because it does converge at x equals -1, just not absolutely. Absolutely at x equals -1 would be the harmonic series, which diverges, which is what we got when x equals +1. Wow, a lot to think about, a lot going on. We're going to do a couple more of these to practice. All right, let's find the exact interval of convergence. For what values of x does my series converge absolutely? For what values of x does it converge conditionally? Okay, so what's my tool? The very powerful ratio test will allow me to find a generalized interval of convergence for a power series. So what will we do? We'll consider the ratio test. That is the limit as n goes to infinity of the absolute value of, and we'll do, oh gosh, we go right to 1, pretty soon. So anytime we're considering the absolute values, right, that just changes to a +1. We don't have to worry about it anymore. So that's just +1 and breaking up my 2 times 2 to the n on the bottom. On top I have 2 to the n, gives me a 1/2 on the bottom. And an x plus 1. There. I get 1x plus 1 quantity on top. Is that what you guys are getting? Everybody do that right? So this is x plus 1 in parentheses times x plus 1 to the n over x plus 1 to the n, and I'll cancel out those x plus 1 to the n, leaving with quantity x plus 1. Okay? Sydney?
Wait, so is there a -1 like on top in the first step?
Yep.
Or does that like cancel stuff out?
Nope. What I did was I said the absolute value of -1 is +1.
Oh, wait, so you just.
So I didn't write it
Okay.
because I know that when I consider the absolute value of the terms, there's no more alternating sign, it's just 1. Grace?
Can you just go straight to knowing that r equals x plus 1 over 2?
Yes. Well, from right here?
Yeah.
As long as you, yes, the absolute value of that, you recognize that as x plus 1 over 2 to the n is geometric with r equals x plus 1 over 2. Yes, absolutely. All right, so what do we need? Converges absolutely when what? When x plus 1 over 2 is less than 1. And Grace recognized that as a geometric series with r equals x plus 1 all over 2. Because we could have rewritten that with exponent rules as x plus 1 over 2 all to the n. So yes, then you could jump right here. Interesting how that, still that 1, right? It's still the same deal. We still need that to be less than 1. Okay, so when does that happen? Well, converges absolutely when that's the case, which means 1/2 is that the case. Which means that my radius of convergence is 2. Are you guys getting a radius of convergence of 2? Which means that the interval on which the series converges is -2 less than x plus 1 less than +2. So I know that the series converges on the interval, right? On the interval, -3 is less than x, is less than 1, yes? And now we just need to consider the endpoints. So what do we do for that? We plug in the x value at each endpoint into the original and make a new series. So we'll say at x equals -3 and consider the new series that's created. So we'll go to the original, n equals 0 to infinity. When x equals -3, -3 plus 1 is -2 to the n over 2 to the n, which equals, oh gosh, so -1 to the n times -2 to the n, isn't that just 2 to the n? And isn't 2 to the n over 2 to the n 1? So we're talking about the sum of the series whose n term is always 1. So this would be 1 plus 1 plus 1 plus 1 plus 1. Does this converge or diverge? Diverges by nth term test, right? The nth term equals 1, which is does not equal 0. So there's no hope of convergence. So diverges by nth term test. Which means, do I include that -3 or not? The -3? So far we've got -3 strictly. Now what do we need to test? We've got to test that 1. Exactly. At x equals exactly 1. Then my series becomes n equals 0 to infinity of -1 to the n. -1 plus 1 is 0. Are you guys getting 0? To the n over 2 to the n.
Isn't it 1 plus 1?
Sorry, 1 plus 1 is 2. That's a lot better. I'm running into the negative part. Wait, I don't remember that. 2 to the n over 2 to the n is 1. So I get 2 to the n over 2 to the n is just 1, and I still have the -1 to the n, don't I? Oh, what does this do? Well, this is -1, plus 1, minus 1, plus 1, minus 1, plus 1, right? Don't be lulled into thinking that that equals 0 or converges, because the nth term, right, does not approach 0. Furthermore, the partial sums would always be oscillating back and forth, either would not converge on a particular thing. And so this diverges as well. Which means that my exact interval of convergence is -3 till 1, parentheses or brackets? Parentheses. Absolutely, for all values of x inside that, -3 to 1, diverges at both x equals -3 and +1. So converges conditionally for what? Nothing. There's no values of x for which this converges conditionally. Yikes. How are we doing? I think we're doing great. I think we've got another one to consider. All right, guys. So as you know, the general tool, right, for determining an interval of convergence for a general power series is the ratio test. So let's go ahead and go after it. Okay? So I got x times x to the n over x to the n, again, reduced, oh, this should just be x. How's that? Is that better? Way better. Is that what you guys are getting? Yes. All right. So as n goes to infinity, can I consider what happens to this n term, right? This rational n squared over n plus 1 squared? Yes, I could expand the bottom and generate n squared plus 2n plus 1. Dominant on top is n squared. Dominant on bottom is also n squared, which means that as n goes to infinity, this rational expression goes to what? 1. So this will converge absolutely when absolute value of x is less than 1. So it converges absolutely on negative 1 to 1. Right? It converges absolutely on negative 1 to 1. But now we need to consider my endpoints. Right? So let's go ahead and consider my endpoints. At x equals negative 1, the series becomes negative 1 to the n over n squared. Negative 1 to the n over n squared, is this going to converge or diverge? Well, this is isn't this the reciprocal squares alternating? So the question is, does this converge? Absolutely? Conditionally? Diverges? This converges by, right, by p series. What about in the, so it's alternating sign, right, alternating series, so this converges. But what about the absolute value? In absolute value, would this converge or diverge? Converge by p series in the absolute value, meaning that negative 1, right, is included not only for convergence, but now it's also included for absolute convergence. And so yes, we include this not only for convergence, but also for converging absolutely, because the absolute value of this series would converge by p series. It would just be 1 over n squared. That converges by p series. And you guys see that that's, when we get it 1 in there too, we'll get the same thing. At x equals 1. We get 1 over n squared. Converges by p series. Converges by p series. Absolutely as well. So I get absolute convergence on all values of x negative 1 to 1. I could still have a square bracket here if this had converged conditionally. I would have a square bracket for interval of convergence, but I would say it converged conditionally at one of the endpoints. Here, I converge absolutely for all x values, negative 1 through 1 inclusive. You guys see that? Hey! Gosh darn it, there's a slide we've been looking for. So what's the difference between absolute and conditional convergence? And describe the possible effects of rearranging the terms in an absolutely convergent versus a conditionally convergent series. Oh, this is good. I like this closure. Mix this stuff up. I'm going to pause and give that just a minute to write that down. So what's true in order for if a series converges absolutely? If a series converges absolutely, right? Then what has to be true? The series, if it converges absolutely, what has to be true? Courtney?
It converges when the absolute value is.
Absolutely. So if we consider the absolute value of the terms, right, then this series of the absolute value terms also converges. So in order for original to converge absolutely, the sum of the terms in absolute value must converge. Versus conditional convergence. Conditional convergence, the series still converges, but it does not converge in the absolute value. So this is where we converge by, and oftentimes you'll see this, it involves an alternating series, right? Alternating series is where this shows up, where it'll converge conditionally, because it converges by alternating series test, but the absolute value of the term doesn't converge. Awesome. Describe the possible effects of rearranging the terms in an absolutely convergent versus a conditionally convergent series. So what are the possible effects from rearrangements of those two? Danny?
For absolute, it's still convergent.
Any rearrangement of an absolutely convergent series still converges to same value, same sum. Good. Versus conditional, Danny?
It can be manipulated to be divergent or converge to any.
Absolutely. We could rearrange a conditionally convergent series such that it diverged or converged to any predetermined sum. Awesome. What questions do you guys have about our closure items today? Guess what? I actually have the OTL items selected and I have a key. I just have to hyperlink the key to Moodle. So I'm a little ahead of the game, but there you guys go for your printout.